So the next unit we're going to be looking at is what's called work and energy. Hugely important. Sorry? Okay. I don't know. I thought somebody said something there. Hugely important to our understanding of physics, but there's a bit of a problem because in this unit we're going to be using words that have different meanings in English than they do in physics, and the first one is work. So in physics, work has a very, 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 very specific meaning. Most of you think that work means tiredness. Oh, if I'm working hard, that means I'm getting tired. That is not the physics definition. If we do work in physics, you do work on an object. You perform work on an object. And for that to occur, two things must happen. A force must act on an object, and the object must move through a distance in the direction of the force. Dom, can you stand up? Seriously? Push against the wall as hard as you can. Seriously, as hard as you can. Now, if I told, keep going, if I had Dom continue to push for like an hour, by the end of that hour, you can stop now, he would be physically tired. He would think, push again. He would think he was doing work. Now, is he applying a force to the wall? Yes. Is the wall moving a distance? He has not done any work in the physics definition. Work is not tiredness. Have a seat, Dom. So the first thing I want to impress upon you is if an object isn't moving, no work is being done. But there is a second key as well. The work and the force must be in the same direction. They must be in the same direction. So, work is a scalar, and it's calculated by it's the force times the distance traveled in the same direction as the force. Kylie, we're never going to write it out that long again, but I'll give you, this is the English definition here. There's actually two other better definitions of work, but they're more complicated. So we're going to start out here, and then we're going to ramp it up over the next few days. But for now, we're going to say, you know what work is? If you apply a force on an object, and that object moves a distance in the direction of the force, you've done work on that object. What's our abbreviation for force? F. What's our abbreviation for distance? D. What would be a good abbreviation for work? Now, that's the equation, FD or F times D. And Brad, I'm not going to remind you that the force and the distance have to be in the same direction. You're going to have to commit that to memory here. In other words, that part of it doesn't actually appear in the equation. It does in the calculus form of the equation. For what it's worth, that looks terrifying, so I'm not going to give you the calculus form. But that one there does imply that there has to be a directional component. Okay? Even though direction is important, work is a scalar. It doesn't have direction. You can't work north. You can't work west. What are the units for work? Well, what are the units for force? Newtons. What are the units for distance? So the units for work are Newton meters, but we've given that a name. We call it a joule. Symbol, capital J. Named after a scientist whose last name was Joule. Work is measured in joules. Okay. Example 1. How much work does it take to lift, important, a 12 kilogram mass from the ground to a height of 9.5 meters? Okay. New equation, work equals force times distance. When you lift something which force are you having to perform effort against? And then typically we often refer to a vertical distance as a height. You could put a D there, Noah. I wouldn't freak out. But later on, this is going to become a useful equation anyhow. The amount of work, now 12 kilograms, about a heavy bowling ball, maybe 2 bowling balls. 9.5 meters, 3 stories. So you know what? Putting a bowling ball on each shoulder and carrying it up a 3 flights of stairs. If you're trying to put it into context, it would be mass 9.8 times 9.5. How many joules of work would a person have to do to accomplish this? 1,117. 1,000 joules of work, yeah, all of you could do it. Now, if I asked you to repeat that over and over and over, okay, you'd start to get fatigued. But it all depends on how fast you do the work as well. If you sprint up the stairs, that would tire you out far quicker than if you walk up the stairs. And you'll notice in this equation, there's no time component. I'll explain to you in a couple of days, Jake, what you think of as getting tired is not doing work. It's generating power. And the faster you generate power, the quicker you'll get tired. So when you say to Mr. Goulet in practice that you're working hard, you're not. You're powering hard. Yes. Dominic pushes against a brick wall as hard as he can for 12 seconds. Amazingly, the wall does not move. How much work has he done? Because there's no distance, 0 joules of work. Pushing a box along the floor requires a steady force of 22.5 newtons. If you push it for 13.6 meters, how much work have you done? Is the force and the direction in the same? Is the force and the distance in the same direction? I think so. If you're sliding something across the floor, that's a nice horizontal floor. I assume, Chris, you'll be applying the force in the same direction that it's moving. So yeah, you have done work. How much force? 22.5 newtons. Distance, 13.6. How many joules of work have been done? Oh, nice fluke. Worked out even. 306 joules of work. Okay. Next page. Dylan pedals his bike up a 19-meter high hill. The combined mass of the bike and the rider is 65 kilograms. The bike requires a steady force to continue up the hill. If the hill is at a 12-degree angle, how much work does Dylan do? Now, this sounds like a very complicated question. I've given you angles. I've given you trig. Here is the beauty. Work is a scalar. What does that mean? When you go up a hill, which force are you having to perform an effort against? What direction is gravity? So let's make a little note here. There's the force of gravity. Did they give me a vertical displacement somewhere in this question? Yep. Oh, where? They told me the height of this hill is 19 meters. Are the height and the force in the same direction? Because work is a scalar, well, they are in the same horizontal plane. They're both vertical. Yeah, force is down, but I'm not going to worry about that right now. They're both vertical. Because it's a scalar, Mark, I don't need to try and figure out what the force up or down the hill is, or how far this distance is, or do any trig. This is one of the very, very lovely things about work. You're going to find that we're going to use work as soon as there's a curvy, yucky path. Our best chance in analyzing the situation is going to be, let's try analyzing it in terms of work and energy. So the amount of work it requires is going to be force times distance. In fact, it's going to be the force of gravity times distance. It's going to be mg times h. It's going to be 65 times 9.8 times 19 . And I get 12,103, I'll go 12,100 joules of work. What if I made the hill steeper but same height? In other words, what if instead the hill looked like this? How many joules of work would that take? Same amount. Now, which hill would be more tiring to ride up? The steep one? Why? Because it's faster. That's what you're going to find is power. Power is how fast you're doing the work, and that is what makes you tired. It's the difference between a nice, shallow set of stairs and climbing a ladder. Ladders will tend to tire you out. Or the stairs at the back field back there. They're nice and shallow. You can probably jog up them pretty easily because they're not very high. They're long, shallow stairs. Compared to what if they had built that as a really, really steep set of stairs with no straightaways, you'd find it much more tiring. Okay? So this is one of the nice characteristics about work. It's a scalar. Force times distance. As long as the force and the distance, I said mark are in the same direction. I really should have said are in the same plane of direction. Okay? What if the force is not constant, but changing? Force times distance only works if the force is not changing, if it's a constant force. And I've been very careful so far, Jake, in the examples that I've given you to keep my force constant. Well, here's our second definition of work. The first is, and this is on your formula sheet, force times distance. The second is, it's also the area under a force versus displacement graph. And here's our example. Here we have a graph, kind of messy because I hand drew it. Shut up. Here's what I want you to notice. It looks like the force is getting bigger because at here the force is 8 newtons, but at here the force looks like 2 newtons. This is not a constant force. So I asked, how much work was done in moving the object from 2 to 5 meters? Well, can I use force times distance? Why not? Okay, so my second definition is, this is going to be a force versus distance graph. It's the area underneath the graph. And I guess if I'm going from 2 meters to 5 meters, it's that area. Now, I always pause here and I ask, because some of you are nerds. First of all, does anybody know what shape that is? Begins with the letter T. It's got 2 parallel sides and 2 sides that aren't parallel. It's called a trapezoid. Okay, I've heard that word. Does anybody, and I've had a kid once or twice know this, for a candy, does anybody know the formula for the area of a trapezoid? There is one. Anyone know it? There's a reason. It's kind of redundant. Because anytime you give me a trapezoid, I can do that. I can turn it into a triangle and a rectangle. Oh, and those ones I know how to find the area of. There is a very cool formula for the area. It has like an A and a B and a B. It's kind of cool, but we don't emphasize it because it's You draw one line and you've reduced it to a problem you already know how to solve. So the total area, Jacob, is going to be area number 1 plus area number 2, right? Let's find area number 1. It's a triangle. Who remembers what's the formula for the area of a triangle? That you should know. It's length times width divided by 2, although it's traditional to go base times height divided by 2, but length times width works just as well. What's the length? What's the base? 3. What's the height? How high? 6. You know what? I think I can do this in my head. It's 18 divided by 2. What's the area of the triangular portion? And area number 2, that looks like a little rectangle. This you should also know. What's the area of a rectangle? Length times width. What's the length of that there rectangle? What's the width of that there rectangle? 2. I would argue I can do this in my head as well. How much work was done in moving this object from location at 2 meters to a location 5 meters away from where we started in your heads? 15 joules of work. So, work is force times distance. Work is also the area under a force versus distance graph, especially when the force is not constant. Hey, Mr. Dueck, when do I know to use this one when they give you a graph? It'll be pretty obvious. Just make sure it's a force versus distance graph. Brad, that you can remember because the formula for work has force and distance in it. Not just any graph. Okay, how much work was done in moving this unknown object 10 meters? Try this one on your own. I'll do it up here. Let's see if we get the same answer. I better double check my arithmetic. Yeah, that's right. I got, yeah, no? Yeah. Now, in a couple of days, we'll also tell you that this also means something else. Our third definition of work has to do with changing an object's energy. We would say you've either raised this object off of the ground or you've caused this object to speed up. You've either gained potential energy or kinetic energy, but that's coming down the pipe. Let's take work equals force times distance, and let's combine that with stuff we did last unit involving friction and free body diagrams. We can do some nice stuff here, like this next example. 124 kilogram mass is being pushed along a floor that has a coefficient of friction of 0.25. The person pushing applies a force of 525 newtons over a distance of 22 meters. Okay. Well, A says, how much work is done by the person pushing? I think that's going to be the force of the push times distance. How big was the push force? 525. Chris, how far was the distance? 22 meters. What's that, folks? Somewhere around 11,000. Sorry?
11,550.
11,550 joules of work. Now, not all of that went into moving the object, because I see that there's some friction. Some of that work was done in just opposing, overcoming, resisting frictions. Now let's start to break it down. B, how much work is done by friction? Well, it seems to me that the work done by friction is going to be the force of friction times distance. You know what? This is a job for a free body diagram. I got room over here. There's the mass. What are the forces acting on this object? What did I say the object was? A box? No, just a mass. What are the forces acting on it? Get the obvious one. What else? It's not sinking into the ground. It's not flying into the air. It looks like there's some kind of an applied force of 525 and friction. Does the question say constant speed or anything like that? I'm going to assume that it's not the same length, that friction arrow isn't the same length as applied. Okay. So how much work is done by friction? I said, well, that's going to be the force of friction times distance. How do I find the force of friction? Oh, the force of friction is what times what? Okay, this is going to be mu times the normal force, and now times distance to turn it into work. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What? Okay, so this is going to be mu mg times distance. I think the work done by friction is going to be, what did I say mu was? 0.25? What did I say the mass was? 124. G, good old 9.8. Distance, Chris says 22. Except, we need to say one more thing. Look at my free body diagram. What direction do I have friction pointing? To the left. What direction is this object moving? To the right. So these directions are in the same plane. However, they're in opposite directions of each other. What would be a good way to show that they're in opposite directions to each other? Chris, we're going to say we're doing negative work. What we're really saying is you're losing energy to friction. It's not a direction. I'm not saying a negative is like down or south. What I'm saying is, oh, this is some energy that's being lost, which is a magnitude. It's not as much as we had before. So it's going to be 0.25 times 124 times 9.8 times 22. Negative 6683.6 joules. And where's the negative coming from? Opposite direction of the motion. The force is in, I should have put that first. Force is in the opposite direction of the motion. Okay. You're losing energy to friction. How much? 6,683.6 joules of energy. Now, you added 11,550. joules of energy. You did that much work. But 6,683.6 of that went into overcoming friction. Whatever's left is the net work that went into the object itself. How could I figure that out? Well, I'm going to write the work push take away the work of friction, but that take away, don't put the negative in twice. Don't put a minus minus so that we get a plus. What I'm saying is, here's how much you did, take away what you lost. What did you lose? 6,683.6, and the reason I know that's the loss is, again, that negative there is saying lost energy. In other words, don't go like this. 11,550 minus 6,683.6. It's that. That negative comes from the fact that we lost energy. Or I could have written it's the work push plus friction as long as I drop the negative in from the friction, but I think this is less confusing. What was the net work done? How much work was left over? Oh, pen stopped working again. Pause the video. How much work was done? Net work is 11,550. Takeaway. Hey, I still have that answer stored on my calculator. 4,866.4 joules of work. Okay. So what is work? Force times distance, or the area under a force versus distance graph. Key idea though, the force and the distance have to be, I'm going to say in the same direction. Really though, Carly, what I mean is in the same plane of direction. But if they're in opposite directions, you just say, oh, you've lost energy. We'll call that negative work. Not negative in terms of up or down, not like direction in the kinematics unit, where negative meant to the left or something. Negative in terms of a magnitude change. You don't have as much as you had before. Is that all right? Homework, no pun intended. Number 1. Number 2. 3 is good. 4 is good. 5 is good. Yeah, so far so good. 6 and 7. I think I picked these questions carefully. Oh yeah, got to do the graph. Only 8 questions, that's all I gave? Okay, I'm going to give you folks about 20 minutes to work on this, and then we're going to start the next lesson, and we'll carry on with it next day.